We talk about speed all the time. 60 miles an hour on the highway, 100-mile-per-hour fastball. But what if I told you that just knowing how fast something is going is, well, it's only half the story? Sometimes one little missing detail can mean the difference between being perfectly safe and being in real danger.
Okay, so picture this. You get a weather alert on your phone. It says a storm is moving at 20 kilometers per hour. So should you run for cover? The simple answer is it depends. And figuring out what it depends on is really the key to this whole explainer.
So, how do we solve this storm problem? We need to find that missing piece of the puzzle. It's something more than just speed, and it's absolutely crucial for understanding how things really move. And that, right there, is our missing piece, the huge difference between speed and velocity. See, speed just tells you how fast, 20 kilometers per hour. But velocity tells you how fast and in what direction. Is that storm moving towards you, or is it moving away from you? That one little detail, the direction, changes everything.
So, to put it simply, velocity is just an object's speed with its direction of motion tacked on. The units look exactly the same, meters per second, kilometers per hour, but adding that direction is what gives velocity its real power. It's the piece of the puzzle we were missing.
Now here's where it gets kind of trippy. An object's velocity can actually change even if its speed stays exactly the same. Think about a race car on a circular track, holding a perfect, steady 100 kilometers per hour. Its speed is constant, right? But because it's always turning, its direction is constantly changing, which means its velocity is also constantly changing. It's the same deal with these escalators. They're moving at the same speed, but since they're going in opposite directions, they have totally different velocities.
Okay, so we've got a handle on speed and direction, but things get even weirder when you realize that how we describe motion depends entirely on our own point of view, or what scientists call our frame of reference.
Let's go back to our storm, but let's upgrade it to a hurricane. If we're just standing still watching from a house, that's our reference point, the situation is pretty clear. The hurricane is coming right for us at 20 kilometers per hour. Simple enough?
But what happens if we change our reference point? Let's say we jump in that car and start driving away from the hurricane at 10 kilometers per hour. Now, from our perspective, the hurricane seems to be closing in at only 10 kilometers per hour. And that house we just left behind, from inside our moving car, it actually looks like it's moving backwards, away from us. See? It's all relative.
And this is a perfect example of a fundamental concept in physics. The source material puts it perfectly. Velocity and position always depend on the point of reference chosen. So the next time you're on the highway and it feels like the car next to you is barely moving, remember, it's all about your perspective.
All right, so we get how to describe motion with velocity. But what about the impact of that motion? What happens when things actually collide? This brings us to a whole new, really powerful idea called momentum.
Let's do a little thought experiment. Imagine a tiny bug and a big car. They are both moving at the exact same velocity, let's say 2 meters per second, straight toward a very fragile vase. Which one is going to smash it? I mean, the answer is totally obvious, right? And that simple fact tells us something huge. Velocity alone isn't the whole story when it comes to collisions. Mass matters. A lot.
So, this combination of an object's mass and its velocity has a name. It's called momentum. The formula is actually beautiful in its simplicity. Momentum, which we represent with the letter P, is just mass times velocity. You can think of it as a measure of an object's unstoppability. The more momentum it has, the harder it is to stop.
And this really drives the point home. Even though they have the same velocity, the car's gigantic mass gives it an insane amount of momentum compared to the tiny bug. That's why one is going to shatter that vase into a million pieces, and the other one, well, it just splats.
For our grand finale, let's set up a fun, kind of weird matchup, a battle of mass versus velocity. Which one has the bigger impact on an object's momentum? Let's find out. So, place your bets. Who do you think has more momentum? In this corner, we've got a massive 6,300 kilogram elephant, just kind of strolling along. And in the other corner, a sleek 50 kilogram dolphin zipping through the water at top speed. So what's it going to be? Huge mass and low velocity, or low mass and high velocity? First up, the elephant. We take its enormous mass, 6,300 kilograms, and we multiply that by its very, very slow walking speed of about 0.11 meters per second.
That gives us a total momentum of 693 kilogram meters per second. Okay, now for the dolphin. Its mass is way smaller, only 50 kilograms. But its velocity is much, much higher at 10.4 meters per second. So we multiply those two together, and its momentum comes out to 520 kilograms meters per second.
And there you have it. The slow-moving elephant actually has more momentum. I have to admit that is not what I would have guessed at first. This is just a perfect illustration of how momentum really works. In this little showdown, the elephant's absolutely gigantic mass more than made up for its super slow speed, giving it the edge and unstoppability over the much, much faster dolphin. So, after all that, here is a final thought I want to leave you with. We've just seen how incredibly important direction is. So why do our highways have speed limits instead of velocity limits? It's a great question, and it really makes you think about how all these physics concepts show up in our everyday lives. Something to ponder on your next drive.